Okay, so hello everyone. We're talking about integrable deformations. Just introduction to integrable deformations. Mostly it will be about integrability and less about deformations. I can also do another talk later, maybe if there's some. If someone wants to know more about it. So the talk will be about talking about what I did, what I learned in summer school, and 2 months ago in Santiago de Compostela. Summer school was about dualities, deformations, and integrability. And today it will be mostly going over to 2 lectures. One was given by Ben Hoare. I'll give you references. They both published lecture notes on archive, so you can search that. So one is this was about integrable deformations, and one was introduction to classical quantum integrability by Ben. So we're going over some parts of these 2 lectures. So it's not going to be like a research talk or anything. I will not go into any results, just what we discussed during those lectures. And so one purpose of this talk is to just say what we did in the summer school, but also to set up for other talks. In 3 weeks, I will be talking about other topic in this summer school, which will be for the Chern-Simons theory. So to understand how is that related, I will introduce some models and some notions today. And then I guess eventually I will also talk about his habilitation thesis, which is also related with this. So you can also think about today as a setup for these 2 talks. It can also be thought as just a standalone talk. So I'll start about integrability. Then I will talk about the principal chiral model, in which I will introduce the notion, in which I will show you how integrability works, and then introduce the notion of deformations, integrable deformations, and then I will shortly talk about spacing models. So I'll start with just the notion of classical level of integrability in the Hamiltonian setup. Which is quite simplified comparing to the other models which we are talking about, but the main point is the same. So if we have some 2 n-dimensional phase space with p's and q's, and if we also have in this setup n functions, let's call them I, that satisfy certain properties, that they are evolved. That means that they cause and commute with each other with respect to cause and predicate. They are independent from each other, so this is index I, which goes from 1 to n, and if they are conserved, that means that their derivative is 0 or equivalently they commute to Hamiltonian. We can use these n functions and solve the equations of motion by quadratures. So we just need finite number of integrals. So sort of the main idea of integrability is to have enough conserved quantities, we call them charges, to help us solve the equations of motion. And
isn't H1 considered as I's?
Yeah, sure. So you basically just n minus 1 functions.
The second condition is superfluous.
No, it's not, because it's only for I equal 1 or 0 it's not necessary, because H is one of them, but you also need all the other ones to commute with H.
What? H can be F1, for example.
Oh, yeah, then this would imply, yeah, sure. If you take it like that, then I guess that you don't need that. If one of them is H, then this condition also has this inside of it. Yeah, that's true. I don't know, maybe in some cases you don't want to take H as one of the functions, but I think you always might.
But yeah, it's true that H is always going to be a function of F1. Yes.
Yeah. So you basically don't need this if you take. Well, if you sort of fix one F to be exactly equal to H, you don't need this because it's already.
When you're looking for these Fi's, you just need to find n-1.
Yeah. Okay.
Independent.
Yeah, sure. So, yeah. Yeah, so one of the canonical examples would be, for example, the harmonic oscillator in, let's say, one dimension, where you just have two coordinates, so the n is 1, and you just need one function, which would be the Hamiltonian, and you can solve the equation. But there is another way how to find these conserved quantities. It's called the Lex method or Wess-Zumino method, which in some sense, in some cases it can be better than this or worse, because here you would have to find n-1 functions that satisfy this. So let's say you can do it, and you want to find some different method. And that is if you can rewrite your Hamilton equations in, let's say, a better form, or some more geometrical maybe way of thinking about them. We need to find two matrices or a pair of matrices we call L and M, such that these equations are equivalent to one equation, that is this. So again, you have to do something, but if you can formulate your problem instead of not using Hamilton equation, but as this one equation for L and M, then you can find these conserved quantities by doing the following procedure. You take Qm, and this is an index, and you trace over the powers of this L matrix. And now I claim that this will be invariant and on shell, of course. So if I do the derivative of this, it's 2m times trace 2m minus 1, which I can plug in from the equations of motion. So I can plug in m, l, 2m minus 1 minus lm, 2m minus 1. And now you can see that this is m times L to 2m. And this also, if I use the cyclicity of the trace by moving to one direction. So cyclically permuting this to ml to m. So these two just trivially cancel, and we get 0, meaning that we do have conserved charges. And now the only thing we need to know about them is if they are in motion. So if they are pulsing commute with each other. And here it is more complicated, or much more complicated, to describe what sort of equation you need, or what sort of formulation you need to, let's say, write down the general condition for L and M, for L in this case. And I will sort of use the end result, and I will introduce some formulation and show you what equation you need for the volatility. So I suppose these L and M are in some matrix algebra, elements of some G, and I'll introduce a matrix in this G, which I'll call R matrix. Shall be like this, R12, or it can just, at this moment, it can just be R, and it's in G times G. And then you can, there is a theorem which says that these charges are in motion. So they satisfy the last condition you need for integrability. If I think it's the Ben Hoare, I'm not sure now that I think this. If this equation is satisfied, so I'm taking this L, I will in a second explain what this 1 and 2 means. And it is the coming. If there exists such an R matrix, that this is satisfied. This is an equation on G times G, meaning that L is just an element of G. So it would not make sense to have this on G times G. So what we have to do is we do a tensor product with the identity, and we can do it two ways. Either we take identity on the first or the second component, and then it's denoted in this index. So L1 is L times identity, L2 is 1 times identity, R12 is your R matrix, which you're trying to find to solve this. It can be expressed in terms of L, but it is a complicated way. You can just think of it as a matrix which I'm trying to find. And R21 is just a composition of R12 with the permutation matrix in G times G. And you can continue this further with this equation and use the Jacobi identity and to sort of eliminate these L's. But now you will find only sufficient condition, which is called the classical Yang-Baxter equation. Now it is only equation for R, but it is on a bigger space. It's on G times G times G. And now there will be sort of the explanation for this notation in R. Why are these indices here? So now we are in G times G times G, and R11 is R12 acts on G times G, and now you times the identity. So R is an element acts on G times G, so it takes two spaces, and we take the first and second, and here is the identity. In this is more complicated. R23 would be identity times normal R. I can also write this without the indices, and I can just say my R. This would be without the indices. It would make sense, and then you would compute these by these rules that it acts on the first and second space, here on the second and third space, and the rest is identity. And now the only problem is this R13. But you can sort of compose permutation operators. This one can be constructed from either this or this by some proposition of permutation operators that would make sense. Yeah, I don't have the correct formula for it now. Should make sense. So, just going back to these charges, we sort of have to reformulate the theory in a way that we are looking at this classical Yang-Baxter equation, and we are looking for R matrices that satisfy this equation. And there should be additional condition which also follows from computation is antisymmetric. And if you can find such an R matrix, then we can Yeah, and then this should, I guess, be satisfied, and we prove that these charges are in evolution. If you want to see how exactly is the R matrix related to this L, it's actually related to the eigenvalues of L and the diagonalization matrix. It is in one of the lectures, I think in the second one, but it is quite a complicated expression. And it is not that important for what I want to do today.
Actually, Stanislav, I think you can, if you want to be more explicit without these permutations, can you, I mean, since the tensor product is always a finite linear compilation of, I forgot what it's called, diodes or something. So you will always be able to write R1, 2 as some finite sum I, and then I1 tensor R I. I guess it's a different so it actually have to be two different so something like so I should actually use two different symbols, something like this. So you will always be able to decompose this, something like this, and then you could then write R1, 2 here as some finite I, and then you get R I1 tensor 1 tensor R. 2 or 3.
I see. Okay.
Right?
Yeah, I think that makes sense. Yeah. I don't know how exactly we find it, but
Right. Yeah. I mean, just in principle.
yeah. In principle. Okay. Thanks. Okay. So I'll shortly just talk about what is the difference in field theory, and then I'll talk about the principal pattern model. So let's imagine we have field theory and plus some dimensions. Now, instead of working with so pair of matrices, we will have well, we will also have a pair of matrices, but we start with some matrix L, and we want it to be well, we can think about it as gauge field. So we want it to be flat in this sense. So that's why this equation. But I have two-dimensional, so I have I'll be X. And that's just some matrix. And you want your equations of motion to be in this way. And if you can do that, then you can again find some conserved charges. Now we will have to do a more complicated way of extracting these charges. If we think of these as gauge fields or as some connection, we can make sense of the parallel transform. Which will be some exponential, which has to be ordered in some sense because these are matrices. So we have to prescribe some sort of ordering because they don't have to commute. So how we want to when we expand the exponential, we need to sort of say which go to the most left and which go to the most right to make sense because they don't have to commute. And we can also use this flatness condition to see that this integral doesn't depend on the path, because if we have some if we have zero curvature, then we can rewrite this as some other matrix.
Where does the set come?
Yeah, I'll say that in 1 second. So Z is what is called a spectral parameter. It's just an extra parameter that you can that these matrices can depend on, and it doesn't change the equation. It's just some auxiliary parameter in the theory, but it will be useful in a sense. So we can define this matrix, which is called the monodromy matrix, and it will be conserved. You calculate the derivative of this, it will just depend on the boundary terms, and if you boundary terms like L, T at 0 equals Z. So if you say this is 0, then this will be conserved, and you have your charges, which you can, which now you can, now you would have like one charge because it's one matrix, but now you can use the spectral parameters, the Z parameter, and expand this. So you also should take the trace of this matrix, and I define small t Z as a trace of 15. And now I can expand this. Z is a complex, I didn't say that. Z is a complex parameter. And I can do an expansion in this parameter, in the powers of this parameter. And I will get my conserved charges this way. So, yeah, this might not be so obvious by this works, but I hope when I show it in an example, it will be more clear. And this is the monodromy. And lastly, just the final point of the setup, if we have quantum integrability.
And the boundary is x equals 0?
Yes. So if I reparameterize the path in such a way that I have 0 and 2 pi, then this will depend on the boundary, and you can take this to be 0 for this to be conserved. So for the T-derivative to be 0, you take the boundary.
Oh, okay.
So in the quantum case, we are going to replace all the Poisson liquids with commutators. Now we are looking for charges that commute with each other. So some quantities, some functions, matrices that commute, operators. And it turns out that if you find your charges that are conserved, then this holds again if and only there exists some R matrix. Now it will be big R because that's how we denote quantum R matrix, which is an operator of the tensor product of Hilbert spaces, which is often denoted schematically like a cross.
Can you see the chart there, the background?
And so if there exists an R matrix, that satisfies the quantum Yang-Baxter equation, which is an analog of the classical one, which was the condition for the integrability, but now it is again using the same notation that they are on some Hilbert space to the third power, and these act trivially on the third component, on the second, and on the first, and not trivially on the others. So this is the quantum Yang-Baxter equation. So it is similar to that. If you can find such R matrix, then it will prove that your charges will be in motion. And you can schematically write this if you care. So this will sort of describe in which spaces the R matrices act on. And the intersections always correspond. So let's say you take the order going up, then you look at the intersections, and they correspond to how these are written in terms of the product, because you have to commute, so you have to be careful about the order. And here you see the 1, 2 first, then you have 1, 3, and then you have 2, 3, and it should be equal to 1, 2, 3, R 2, 3 times R 1, 3 times R 2, 3, but we should also have some interpretation in terms of scattering in, let's say, quantum field theory. That there is some relationship between the scattering matrices and these R matrices, and you can think of these as some scattering amplitudes. And then this would be like some condition on the scattering amplitudes to for your theory to be integrable. And you can also find some correspondence between the quantum R matrix and the classical R matrix. And you can expand this in powers of H bar. It will be something like 1 plus H bar times R. And this is the classical Yang-Baxter equation. And if you were to plug this in here, calculate, then you will get that this is something which is 0 times H 0, something greater than 0 times H to the first, and then here we would find the classical Yang-Baxter equation for H squared. There is a correspondence between these. That is enough for the setup, or just find some basic quantities. And now I will show how these things works in the principal chiral model. And then I will also talk about the deformations of the model. So or in short, PCM. So that is a two-dimensional sigma plot. It doesn't have to be two-dimensional. We will take two-dimensional sigma model. That means that it is just a map within some 2D space, which our coordinates connect. And the special thing about this principal chiral model is that the target space is some group. And so this group element is some group G. For our cases, we will take G to be simple. But it also means that we have the killing form and invariant linear form on the Lie algebra. And so the model is described by an action which has the fundamental field in it called the chiral chain with one space-time index, so mu is T and X, and it is defined as the fullback of the Maurer-Kaplan form on the Lie algebra. Well, these are the components of the fullback. You can have dx mu, and it will be a one form on, and this is like the space sigma. And this is the fullback of the Maurer-Kaplan form. It's a Lie algebra with one form, or components of it. It's written like that. And the action.
I guess there's no comma in which means.
Yeah. Thanks. We have some coupling constant H and action. We use this invariant one form and trace over these Maurer-Kaplan forms. So it's some, let's say, you have a flat connection on the Lie algebra, and you just use your map G to pull it back to your space, so you can integrate over. You can integrate it over your Lie space. And this model has a global symmetry, which is by constant multiplications of elements in G. So the main field G, which is also here in direction, which is written in terms of their derivatives, can be multiplied by some two constant matrices from the group, chiral and GR. So we have two copies of G. You can either act from the left or from the right or both, and it preserves this action. Because everything, if it's constant, then we don't care about the derivative, and everything is written in terms of G to minus first times G. Okay, so we can calculate the equations of motion. So we can do a variation. I can do a special variation that I take G and I take an infinitesimal variation by some element in the Lie algebra. Epsilon is in the Lie algebra G. And so small g is an element of the group, and small g with this line is the Lie algebra of the group. And we can see what is the. I'll just do some calculations so we get more familiar with the moment. If I will be running out of time, I will be skipping calculations later. So I'll just do variation of 1j because they are contracted, so it will just multiply by 2 if I do the other one.
But I guess it should be GR minus first if you want to think of it as an action from left.
Yeah, probably. Okay. Yeah, I'm doing both things at once here,
Sure.
but I guess they can be independent.
They,
Yeah, they are independent. So
Of course,
I just wrote them. Yeah, well, I could write it like this, right? There are two actions.
yeah, I mean, it's just a definition of a group action.
Yeah, but
But of course, you can have left or right group action, but
You have a group G times G and you act on G.
Yeah.
And in order to have a left G times G action, you have to have GR minus.
exactly. Of course, you can have a right group action and then the minus first is something else.
yeah. Yeah, that makes sense. Okay, so yeah, thank you. And I'll just do this calculation. Yeah, so I'm just using the delta x like derivation. And what I will try to do, I'll just try to take d of delta of g out of everything. But here I'm also using that I'm using just an infinitesimal variation. So I'll, instead of labeling everything as delta g, I'll just have epsilon, which takes care of everything. The only non-trivial thing I have to do is, well, I have to know that I can switch these two, and I'll just have to calculate what this is. But that is the standard trick that I take g times g minus first with this identity, and I do a delta of this. So I have the delta g times g minus first equals minus g times delta g minus first, and acting from the left with g to the minus first, I get this prescription for delta g to the minus first, and then I'll just say that delta g is epsilon times g. So I write everything in terms of epsilon, and I get this. Here I would use the Leibniz rule. So I would get one term where I have g to the minus first g times epsilon, but that's epsilon from the right. And here I have the same term with the minus, but epsilon from the left. But I can write that just as a commutator of g mu and epsilon. And if it's on the right, it's with plus. If it's on the left, it's with minus. So I'll wait. So it would be G mu. No, it's fine. Yeah, it's fine. Right? Plus here I act with the derivative for epsilon, and this cancels, so I have just d mu. So that means that the variation of the action, that's just 2 times that inside of the trace. Dx squared and trace d mu. I was doing the first one plus j mu epsilon times j mu. So that's the variation of this times this. And now we will just want to use integration by parts, partial integration, get rid of the boundary term to move this derivative of it's supposed to be epsilon here, move this derivative here, and here we can use the invariance of the trace. That if I have a trace of 2 objects and there is a commutator 1, I can switch these two because it's the killing form. So this will be trace of epsilon times d mu j mu plus the commutator mu. So I get my equation of motion. Of course, I want this to be 0 for all epsilon, so I want this vector to be 0. But there is a redundancy in the equations, the same as we do now, because if you remember the definition of J as the pullback of the Mallar-Cartan form, then this is trivially 0 because the Mallar-Cartan form is flat, so it satisfies a certain equation, which is like this. And remember the sign relating. This is the equation that is trivially satisfied by J if it's in this form, then it is there's this flatness equation. I think it's like with this sign.
The last thing to say is it's a commutator of the non-abelian itself.
Yeah, that's true. Yeah.
If you're tracking them, one image should be up, or one should be wrong.
Yeah, but it can also be seen from here because if you take them, this is the same. This. Yeah, but you're right. If I have the same thing, then I just go with each other. That's 0. Yeah, so I don't have to use them. So we just have the conservation equation for the J. So we're sort of seeing some similar things as we saw before. That we have some conservation. And it turns out that if you have these 2 equations, the conservation and the flatness of this charge, of this current, you can write some analog of this Lax connection. To keep up with the lecture notes, I will just write everything in terms of the light cone gauge, which makes it simple. So instead of TNX, I will be using x plus and minus, and Lagrangian will be instead of j mu will be j mu plus j minus. The equations of motion will be so that's the conservation equation, and now the flatness equation is with the minus and the equation. It's just a rewriting of what I have here into the light cone coordinates. And if we have these 2 satisfied, we can write down the Lax connection like this by just adding this spectral parameter 1 plus minus plus z. Z is a convex line. What this will do, it will, if I compute the equation for the flatness of this connection, minus or plus, minus. Yeah, if I would just plug this in, I would get something like 1 minus x squared times I will get j plus j minus minus j plus j plus.
So is it L plus minus on the left hand side of that equation?
Yes, thank you, that's true. Minus the z times e plus. So it is a neat way how to combine both equations into one. And you see my equation here, times the z and the other equation here. So if this is flat, we can know if this is both constant and flat. But it allows us to expand this in terms of the z parameter. Well, I won't be expanding exactly that, but the model of the matrix constructed from that, and that allows us to find the constant charges. So I will construct something that I was doing previously. Field theory case for the monodromy matrix, which depends on T and Z. Now it is clear how this Z is introduced. Maybe before it was just an auxiliary parameter, but here is a completely fine prescription. I'll have to again some ordered exponential, half order of the x component. Here it is better to write it in non-linear coordinates, but we can think about this as just 1/2 L plus minus L minus. And this is again some boundary term, so we can say it's 0 if we impose some conditions on L, that it vanishes as x goes to plus minus infinity. And if we from the expression above, we have some formula for Lx in terms of small j's. J plus 1 and we can expand this in powers of 1 over z, and we can also expand the exponential. So I can expand this whole thing in terms of powers of 1 over z and get something like this. And here we will pick up the constant quantities with these powers. We will have some nether charges corresponding to symmetries of the model, the left-hand symmetry. X, J, T. And then we will have an infinite expansion here, and we will get some higher charges which don't correspond to just the symmetries, but they will be conserved because the T of this doesn't depend on Z, so everything should have a 0 derivative. And you can also get some other charges. These are if we introduce the Lorentz group into this, and we can sort of compute the charge of these spins under the Lorentz group, will be the spin, and this will all have spin 0, and we can have some higher spin charges, which will be constructed by similar procedures we had before. It will be traces of powers of these fields. So if I take j plus to the n power and I trace it, and I get some infinite many of these, and I can do the same with minus. This will also be conserved, and the interesting case is, for example, for n equals 2, we just get components of the stress energy tensor. Plus plus and minus minus. Because it is traceless, the other components are 0. The mixed components are 0, and this is proportional to ratio plus the squares of these. So yeah, we get, for example, the stress energy tensor for, and the charges constructed from these are just by doing the integral. There is this spin, which is just n minus 1, and I'll just bring integrals of these. Yeah, so we see the necessary gradients which I described in the theory part to sort of convince us that this model is integrable. In the sense that it possesses enough charges which are conserved. I guess they should also be wrote with. I don't know if that is obvious from that, but we should check it. You know, if the involvability of this is just trivially false, or it should do something.
No, I don't think it's always right.
Yeah.
Fine, on it.
Yeah, you should do everything with the R matrices before to actually confirm that these are involved. I don't prepare that. So yeah, we don't do it on the lecture, so I have an excuse. What we can do next is
Why are you shifting Q to n minus 1? It's just convention.
it's just convention if you
And you call it S?
yeah, like the spin.
Oh, okay. Spin.
We can add something to the model called the Wess-Zumino-Witten to just sort of change the model in a way that doesn't really change direction, because it will correspond to boundary term, but we have to add an additional auxiliary dimension by, let's say, we start in R2. Our model is in R2. We will compactify that by the one-point compactification to a sphere. And then we would think of this sphere as being the boundary of the ball. And we would have to extend the field from the boundary to S to G, extend to field from the whole thing. That is, of course, equal to our previous field on the boundary. We can do that for simple Lie groups because the second homotopy group is stereo. So it is possible, this should be well defined. And we can add now to our previous action something for the Wess-Zumino term, which is additional coupling constant, another coupling constant called G, but it is now an integral over the whole thing, over the ball. But we will see that it will have some total derivative term, which we will add by Stokes' theorem to the boundary. We are still interested in the boundary in our previous space. This is just like an auxiliary bulk space that is there just not to sort of create another theory.
Actually, didn't you say that the Lie group was simple?
Yes.
Oh, this is, yes.
So we should have this
Yes,
trivial. Yes, this should work for simple. I don't know, maybe they also.
No, you're right. It doesn't do.
Even for
X2, you need X2.
Even for semi-simple.
Yeah, well, it should be, it's the higher ones. I mean, simple is not enough. Well, it is enough because it follows from H2 of G. It's okay.
But maybe this would make sense even for some other groups if we sort of do it differently, I guess. I don't know if these Wess-Zumino models are just constrained to simple or semi-simple groups. Maybe it somehow works for other groups. But maybe only a formal sense or something.
Yeah, I guess the problem is the first problem is I guess is if the killing metric is not. No,
No, the problem is the extension, right? If
Yeah,
you
doesn't have to be theory or something.
also that, yeah. Yeah, but even before Wess-Zumino, whether it makes sense, the chiral model.
Yeah. You would have to. Yeah. That's true. Maybe you can write down some different actions for them. You always would have the Mauritian form, right? But sort of.
Yeah, I
You
guess when
can't
you,
really create something quadratic out of it if you don't have the joint form.
yeah, you have a degenerate killing, degenerate form, and it could be that you cannot see all directions.
I see. I'll just check the values. We can sort of sketch the equations of motion. I prepared the whole equation. There is a lecture in 1 hour for Norbert, so it would take too much. But yeah, let's say we try this. I will have the full action of both of these models. I will have the previous term and this, and I will try to compute the variation of that. Yeah, so I'll just write that in terms of the J plus and J minus. Yes, sorry. What I didn't say is that we have now two types of indices. Plus minus or mu, which is just 1, 2, or just plus minus, and ijk is for the three-dimensional space, so it's 1, 2, 3. Yeah, there's no need to put corner. So we already computed this. So this is just minus h2 d2x. There's epsilon. I'm doing the variation, so we computed that. Again, I can use the same prescription for the infinitesimal variation as before. Equals j plus. Again, the commutator is 0, and here it will be more complicated. So we can use the sequencing of the days and this epsilon tensor to see that the variation of each of these will just give me the same thing. So I can just do variation of 1 and multiply by 3. And we know what variation of j is. Now it's just the infinity and the different indices. So it is di epsilon plus ji epsilon. And now we will use this derivative and integrate by parts, but we will keep the boundary term. So I'll just,
And I guess there's a factor 3. Oh yeah, that's 6.
yeah, that's 1 over 6, and just multiply by 3. So keep the first term, and here I will integrate by parts, but I will keep the boundary term. Because that is the part of what we added that will affect our previous model that will be exactly this boundary term. So this is the not the boundary term, it's the integration by parts. So that's the part that is derivative here. Again, I'm using the invariance of the killing form by switching this epsilon with this whole thing. What is the property of the this works under the trace, right? Under the traces. I can do that. And maybe that's one bracket. And this is 0 because it is contracted with the epsilon tensor. And that is just how you can write the Jacobi identity. And this is also 0 for different reason.
They're not separate. This.
Okay, yeah, maybe.
If you use the flatness of J,
Yeah.
the first one instead of the second one.
Oh, I see. Yeah.
And there's a sign.
And this is not just the divided with the Jacobi. Yeah. Okay, then you have to use the flatness. Yeah, but this term is not the important one. The important one is the total derivative term, the boundary term, which is just the same thing, but in front of the trace. Some just what we have left, so let's just that. JJ. And now I can use, so this will go to 0 by using the flatness of J and I guess the Jacobi identity, and they have to combine in a way to get 0. So by using the
You're right, they're separate. This
yeah,
you definitely use the flatness.
you use the flatness condition to write this derivative as to write this commutator as a derivative, so that would be djjk minus dkjj. That's the flatness condition, and now you can see that there is double derivatives here, and there is an epsilon tensor here. So the derivatives commute. Both. So if I can act either there's a bracket here, I act in here and here, but in ij this is antisymmetric, and in ik this is also antisymmetric. So this goes to 0 by using the flatness, and then by using this epsilon tensor. And then I think that this is just the Jacobi. But maybe I'm missing something. But I think this should just be 0 by the Jacobi.
Yeah.
But Ji
Yes.
is
Yeah, well, we assume, I guess, that the extended J also satisfies.
yes.
That's
That's it.
I don't
So
know.
there are three
Yeah.
kind of. What does it mean?
Well, I guess it would be.
It's just defined on the, it's just a fallback.
It might be like a different.
So you have okay. So you have
Define it in the fallback.
So you have S2 immersed in some wall,
Yeah.
the boundary, and then you have a map from the wall to
You have two
the
maps.
groove.
You pull back just the same one, but to different places. So if
No.
You take the mark and don't group the whole apart
yeah,
to the whole wall.
yeah. So it has to satisfy the flatness because the marker for the G is the same for both maps, and you know the marker
But
is
pullback
flat.
goes the other way.
So
So you pull back from G.
G will be like
Yes.
C, and GI be the same thing. And this would be like the extended G. And these marker forms would be the same because they are both on the algebra of G.
And the flat by construction.
Yeah.
Yeah. That's right.
And because you have the map, you have the whole outcome.
Okay, so
Okay, you don't have what you don't have is that when you have a map from B3 to G, which satisfies the flatness condition, doesn't automatically define the Malevich. Right? If you have some map from
Go the other way,
S2 to this G, then that would even define the Malevich. So the ground is the other way. But you don't need to.
yeah, so here we have now just the two-dimensional integral, and yeah, I'll just take this term and see what it gives under Stokes theorem. You get you just get so yeah, you basically get rid of the derivative and one dimension, but you have to sort of change the indices in a way that makes sense. But this should be fine because it is basically like a derivative of a two form, and then you just divide the two form. But this will add with this and create a new equation, so it will be changed by this converter, and I'll just write what you get. Because now it's just this thing. I should just
Shouldn't H be K there?
yeah. Thanks. Well, now the next step will be just to rewrite epsilon and j in terms of plus and minus, and you get something like this: k on h times j. You get the conservation equation, but it is not really a conservation equation because of these factors. So this parent itself is not conserved because it is still flat because it is the pullback of the Markov transform. But to create a Lex connection, we need something that satisfies exactly the conservation equation, not some deformation of it with this parameter k. So we need to define some new kinds. That is not that difficult. That would be both conserved and flat. And it's just 5 times plus k over h j. Yeah, I just divide them by this, and if I were to plug this on the other side and plug it here, I will get a conservation of j. And this j Yeah, and from the flatness of J and this definition, it is also flat. Satisfied. And then if we have a current that satisfies this O2, we can go to what we did previously and define this Lax connection which required for everything that give us. It's basically reduced to this 1 over Z expansion, and you have everything you need to find the constant charges. So that is pretty much the story of the model itself and how it works in terms of finding the integrability of it, or convincing yourself of the integrability. And now I will talk about the Yang-Baxter deformation of this model. So if we have this PCM model, we have some Lie. Now we would want some R matrix, and here it would be just a constant matrix acting from the algebra. So it could be also times element in G times G dual, I guess. And we can define the deformation of the model. So what do I mean by that? It means that I just take Lagrangian of the model of the PCM, and I do something to it, which I will parameterize by some parameter. And if the parameter is 0, I should return to the original model. So I also to add this operator here, 1 minus eta times R, or I should be acting over this current. So this is in G, so this is fine. And if eta is 0, then I get my original model. You can think of it as an expansion in eta, and it creates a deformation of this model. It preserves the GR, the right acting group, but it doesn't preserve the left acting group because it acts only on one of the components. So we sort of break certain part of the symmetry. Basically, what you're doing is you're breaking GR times G left into GR times subgroup of GL.
Don't you want to write DGL times GR just for logic?
What? Like DG?
GL cross G, isn't that more logical?
Sure. One is on the left. Yeah, so and G0 is just a subgroup of GL that commutes with this, so it should be okay. That it would still preserve that.
How do we see that you break the left and not the right? What is the? Oh, it's because I is some kind of operator.
under the right action. The J's themselves are invariant under the right action, so that's certainly not wrong. But the left action will.
Because
they
they
are
are
conjugation on the J. And that will not necessarily conjugate with R.
Yeah, only the subgroup that commutes is okay. And so again, we just want to ask the same question: is this model integrable? And for that, we would want to find a flat conserved current. So if I write it into motion, it will be again very similar to what I had over there. There will be the terms of these small j's, but they will not be exactly a flatness condition or sorry, conservation condition.
But strictly speaking, I think it's the other way around. GR that's broken in G. Yeah, so, but the way you define it, right?
but yeah, I still don't understand because don't you want this to go on the other side?
So yeah, so these are like the right.
Oh, you're right. One is going through the G derivative. Yeah, so that's not touched. You're right. And the other one has to go the other way around.
Yes. You want the left invariant one.
Yeah, so J and the left invariant one.
It depends on the way you define them previously.
I think,
Yeah, exactly. Whether it's G minus first or you have G minus first.
I think we have the left invariant one first. So it should be.
Yeah, then it's automatically left invariant. Yeah.
No, oh, okay, yeah, I defined that as G. And G minus first, B, G.
Right. So then it's automatically left invariant. Yeah.
Yeah. So, like this. So the change. And so I can write the equations of motion again using some new current. So I'm just doing two steps, in one. I would write it using this J, but it would have some ugly things, so instead I write it in terms of this big J, and I'll just define this. G plus. Where this transposition is with respect to the Kelly form. No, we transpose this for the plus. Plus minus. Transpose this. And now,
So I guess there's also a Yang-Baxter Wess-Zumino-Witten here.
no.
Why did you then change little j to capital J?
Yeah, it's like a different.
Oh, okay.
It's
Okay.
because the little j here is not concerned because of this.
I take it back. Good.
So the big J is concerned and flat. Simple. Well, no, sorry, it's not that simple, but it is. So now we want to see if it is flat from flatness of J. And so I'll just take this and this, put it on the other side, write down the equation for flatness of J, and see what it gives me in terms of this and this.
And I guess it should be D plus instead of D minus, J minus in the equation of motion.
Yeah.
But, plus that.
Yeah, thanks. And what I get is it's not quite complicated equation. Oh yeah, I should put 1/(x) sign here. It's important. So this is an equation for the flatness of the small j's, which is true. And we are trying to see what it gives us for the big j's, for the deformed currents. And it will be sort of more equations at once because we have these parameters which separate these equations.
Is that transposed on R?
Yeah.
Oh, okay.
Otherwise, it would be 2R.
Yes.
And now there is the classical Yang-Baxter equation. This response J plus R J minus R J plus J minus and minus end of the bracket minus xi squared J plus J minus. So if we want this equation to vanish for all parameters psi eta, we just get three equations.
So don't you want a plus in the first parentheses?
I don't know if I want an additional equation or I want to get the same thing as before. Because this can combine with this. Yes, okay. What we want? I don't think so.
So you
Because I want to get the flatness of the J, right? And that would be this, and either one of these two terms, I guess. But they are in the wrong parameter.
Oh, so that's why you need the one of the side
Yeah.
to scale it.
Maybe I just forgot to write it here, but maybe there is also the question, but I'm not sure. Do you know?
Well, psi should become fixed. I don't remember. And what do we want?
Yeah, well, so what we want is
Totally correct.
and what we want are two equations for sure. So we want this, we want the classical Yang-Baxter equation, which I wrote before with these arithmetics. Yeah, I wrote it. And that would be this, what we wrote is here. This. And there is like a modification to the equation which you can do by some constant parametric sign. We want the R matrix to be antisymmetric, that is here, and then we would want the J to be flat, right? So maybe I would have to get it from here, because
Yeah, I think the first.
Yeah, that's
the
actually-
last
that's
term
okay.
should combine- The
That's
last term
okay,
will combine
exactly.
both with the first term and the.
Right, because you need psi squared in front of J plus. It's okay.
yeah, so I can like split it in half or something. Or I can do it like this, and then what you would also need to do is sort of rescale these terms psi and eta, and then this term should combine both with this and with this to give me. So the equations I would have is the classical Yang-Baxter for R, that R is antisymmetric, and J. So the moral of the story is that we started with some arbitrary matrix that just deforms our model, but if we want to keep the integrability of the model, it cannot be just some arbitrary matrix. It has to be an R matrix. So it has to satisfy these two equations for the model to have a flat constant current that would give rise to a Lex connection, which would prove its integrability. Okay. So there is also an alternative way of proving the integrability of this Yang-Baxter deform model, which I will just sketch how it works. That is using non-abelian duality. So instead of starting with let's say the action for this with eta equals 0, I can start with action where I have just some H fields, A plus and A minus, and I add a constraint, a Lagrange multiplier, some element in the Lie algebra that says that the field strength of A vanishes. So if I were to do equations of motion of this, if I would vary this new Lagrange multiplier, I would just get the F plus minus, where F plus minus is just the field strength, E plus and minus. Yes. With either plus or minus, minus equals.
Minus. Just like in a flat formation.
Yeah, oh,
B minus B plus.
and so if this is 0, then you can solve it by the field gauge. By taking the field gauge, which is just saying that there is some G such that A plus minus is G inverse A plus minus G, which would return you to the original model. But what you can also do, that's the non-abelian T-duality part, is you solve the equations of motion with respect to A, and you keep as a new as your new field.
So I guess F plus minus should really be the order for its.
Yeah. Like this to be correct. You can solve for A in terms of nu, and you get the equations of motion, which is by just doing variation with respect to A. So what I will do next is that I will just, let's say, expand everything in terms of the generators. I will get an Lie algebra index on everything because and I will write this in terms of the structure constants, and I will take everything that has AR on one side and just divide by the rest, and I will get something like this. And these are the structure constants. They are contracted with one index, and the other two are RNS. And this has to be, no, not like this. This has to be to the minus first because I'm dividing by it, and this. And I get like a dualized action for the model in terms of new variables. New. Which looks similar to that, but it's not exactly the Yang-Baxter model yet. It is just the first step. You can show that the Yang-Baxter deformation of the principal Chern model is selected by something like a non-abelian T-duality, but there's like 2 more steps that you need to do, but unfortunately don't have time. But I will just,
Can you say it in words?
yeah, I'll just sketch what you would have to do. So instead of doing the dualizing procedure on the whole algebra, just like taking the whole algebra, taking US in the whole algebra, you can just do a dualization of only part of the coordinates. So we have some subgroup of G, and you would just dualize with respect to that subgroup, and you would require there to exist a certain matrix in your subgroup, in the algebra, sorry. So something like this that satisfies certain equations, or you can say it satisfies 2 co-cycle condition. And you would have to add this, and it's supposed to be a closed form. So it's a closed form. You can add it to the action because it is closed. It will not change the action. And so you first need to deform the model.
Should it be direct sum or tensor product?
Well, if it's a tensor product of the groups, then it will be direct sum.
You mean the algebras?
Yes. These are the algebras.
Right.
So it can be like that. Yeah, I'm not sure.
Only there is a 2.
Yeah, it's so what is it the direct sum of G's or the tensor product? Which it can be, because if you have something, some operator of the group, right? It's like a tensor product.
Algebra.
Yeah, but if I think about the algebra as to
Yes,
the section
it's
space
like
to.
it's a two cosine.
Yeah.
So maybe it's more like a conic product.
It's just, yeah, I guess it makes sense.
Anyway.
Yeah, I guess it's kind of good.
Yeah.
Anyway,
Okay.
gotcha.
So you would need to deform that action by adding, let's say, some parameter, psi, omega, and g, would add that to an action. So you first need to add this principal variable. And then you would prefer the non-abelian T-duality on this group, and then you can, so there's not that much space. Then you could identify omega with r to the minus first, or omega to the minus first is r, and a with g in some sense. You would have to do, let's say, with some k subgroup by some non-linear field redefinition. And then it would have the right form of the Yang-Baxter method after you do these steps.
So
So,
you need a sub-algebra which admits a two co-cycle, which is invertible, non-linear.
yeah. So you need some, special conditions of this subalgebra, and also classifying these subalgebras.
Or maybe need it's a sufficient condition at least.
Yeah.
I guess it's more it's not we don't know about necessary, but it's at least sufficient.
I don't know. I guess so. Yeah. Right.
Necessary for this particular construction.
Yeah. And so, for example, by classifying all these subalgebras, you could classify all possible Yang-Baxter deformations. And once you would write your Yang-Baxter deformation like this, it would be sort of trivial to check the integrability preservation, because non-abelian T-duality preserves integrability. Okay, so I'll just use like last 5 to 10 minutes to talk about string form. So the principal chiral rule is not really a consistent model of sigma rule for the string. It is in 2D, which is fine, but it doesn't preserve conformal invariance in the quantum level. So you would need something else. I'll just write down like a generic action, polar confliction for the string with a B field. You can also write down the principal chiral rule by using coordinates on the group manifold and some metric in this form. So you can do it. I just have big G on the target space, indexes on the target space. X is a field from the worldsheet to some target space, and I have metrics on both, and big fields on both spaces.
Well, there are two x's there that are different.
Yeah,
You're
yeah.
integrating over an x.
Small x, just small.
Sigma. Sorry. And so this action is deformism invariant to the invariant because it's constructed of it's a scalar, and it's real invariant, which is that if you scale the metric by some positive function, which can, for example, be represented by exponential of some function, it doesn't change. Because, yeah, so this is an interesting thing. For example, if you were to do a generic sigma model not in 2D, you would just write this same action in n dimensions, and everything will be the same because the indices will just be 4, and we would say when this is symmetric, you will get a condition that d, the dimension has to be 2. So only in 2 dimensions this exact action has the way symmetric, because of the determinant cancels the inverse metric here. And so if you scale it by power of 2, this scales it to 1/2 of 2, and this is -1. So it cancels exactly. And you can think of these G and B as functions of coordinates x vectors for the target space coordinates. And you can further expand to get an infinite series of basically what will be coupling constants. Coupling constants. But that will be the coefficients in the Taylor expansion. And if you were to check the Weyl invariance of this theory, if something depends on the scale, this coupling constants in principle could depend on the length scale or the energy scale, and this dependence is captured in the beta functions. But for conformal invariance, which is some mixture of these two, we don't want these coupling constants to depend on the length or energy scale. So we want all the beta functions to vanish. So to get the consistent theory, we get an infinitely many equations of this type, that beta functions are 0. And for example, the first condition is put like this. First 3 equations. For the theory to be consistent, we also need to add a scalar field, which works as a normalization counter term called the dilaton, and it is phi, which will enter the action, and we get basically a generalization of Einstein field equations as conditions on this Weyl invariance. And we will have where H is derivative of B, antisymmetric derivative. B, you can think of B as a 2 form, and H would be dB. And so you can also encode these equations in a different way by finding an action which will give you these as these equations of motion by some variational principle. It's called the low energy effective action. And it is, I'll just break the Lagrangian because there's some constants. There should also be the Lagrangian, just to save some time. H squared, well, it will be squaring of all the indices plus the m squared again, this will just be contacted. So it is some generalization of the Einstein-Hilbert action with these 2 additional fields. And you can think about if I write the whole action, this is on the target space. So it is in 26 dimensions, let's say, for the bosonic string. And now there is x correctly here, because it's in the target space. And now you can think about this as a new theory. So you just have an action on the target space, and your main fields are metric, the B field, and a scalar dilaton. And these are the invariant curvatures, or something like curvatures. And you can perform a Yang-Baxter deformation on this model. So you can, if there is some conditions, and the conditions are that there should be some vectors or some isometries of these background fields. So you should have some geometries. And the deformation looks like this, is that you take your new, these are the new metric and B field created from the old ones by multiplying it with 1 plus, again, some parameter eta, a matrix theta, and G plus B. This whole thing minus first. The theta is a space-time indices. It's constructed from these scaling vectors, which forms some algebra. And on this algebra, we have defined the R matrix. So again, we write it in the form which has an R matrix because we will then, if we want to preserve integrability, or if we want to preserve the equations, we will get some conditions on this, which are equivalent to the classical Yang-Baxter equations. And K's are defined from the linear G0. So there are scaling vectors of the geometric and the B field. And yeah, so what you can do is you can plug in this into the equation, so you can get new metric, new B field, and you will and you can also get new duality by taking trace or determinant of something. You can get it from this, and you can see how everything changes, and you will see that if you impose some conditions, there is one condition on this theta matrix, which is called the unimodularity condition, or on the R, the trace with the structure constants of this isometry group vanishes, and the classical Yang-Baxter equation, then this will not change. But the calculation is quite complicated. And for example, if you use the double field theory formalism, which we use, then the change becomes trivial. That is, if you write everything in these double coordinates and double field, then the action itself is manifestly invariant for unimodular Yang-Baxter deformations. So yeah, that would be just sort of motivation to look at this double field theory and think about it, because, for example, in this case, it just makes something difficult very, very trivial. Yeah, so to summarize, I was just talking about some models, how to see they are integrable, and a little bit to see how the deformations can preserve, or what are the conditions to preserve integrability. And I guess in three weeks or something like that, you'll see some additional things from the summer school about how you can alternatively derive these models, the PCM and the Yang-Baxter deformation of it from 4-dimensional Chern-Simons by reducing, by integrating out some special directions. You will create a 2D theory which will be exactly this principal chiral model and its deformation. And then that is for the next thing, and that's everything for you today. So please feel free if you have some questions or want to clarify something more. You can ask. And thanks.
Okay, thank you, Stanislav. If there are any questions?
How are we doing the time?
14:43. We have like 15 minutes.
Yes, so
So are there are probably some specific examples worked out for SU2,
Yes.
like that.
Specifically for SU2, it is done in the lecture notes which I put in the archive numbers in the beginning.
And does one get when one gets some integrable partial differential equations?
Oh, I don't know if it's like that, but I think it should be, yeah. Yeah, you know, dual integrability is used in many different contexts. I think it should match the integrative PDEs.
Just to get the logic straight, how did you get the dilaton out of?
I didn't say it really, but you have to define it as some like a counter term to account for some it's like the wild anomaly, right? With the Ricci how exactly does it work? You have to account for the wild anomaly to cancel the the scalar point. Yeah.
Yeah, so in this Yang-Baxter deformation, you can guess the formula that works. These is where you guess this by T-duality. It's a combination of the square root of the determinant of the metric times, so whatever the metric is, the square root of the determinant of the metric, which should be there in the measuring the only effective action times e to the minus 5. That's invariant in the T-duality. So you can guess that that combination is going to be invariant. Then you can extract what phi tilde should be in terms of G shape. And then you can see that it works. That's the easiest.
Yeah, if you're interested in how this Yang-Baxter deformation changes or doesn't change the action in higher orders in alpha prime, like the next beta functions and stuff like that, and that is what Linus is doing in this adaptation. But that has to be done using the double field theory from Wess-Zumino. It doesn't have to be, but it is much simpler in that case. Recording.